Hi folks, today I bring a SANYO panel pair-ups from the Beta VCR6310, judging by the position of the two LEDs and the button above them. The family of these videos is extensive, but must have 8 buttons in a row like the VTC 6500. Our panel has 7 buttons. If anyone identifies it, please leave it in the comments. The goal is to bring the panel to life in as few steps as possible, so the first attempt is to identify the driver, which in this case is one MP1539. I had no luck finding the datasheet, so I had to go by the similarities only. We started with one from the TMS 1000 family, also from the Texas Instrument, and comparing the pinout we arrived at the TMS 1100. We researched the schematics of the SANYO branded VCRs from that era, and again, in the comparison, the closest we came up with has the VTC 5150 models, which use one MP1537, and that is the model we worked with. The most important thing to highlight is the detail that can go unnoticed and lead to the deterioration of the integrated system when it is powered. If you pay attention, they use the designations VSS and VDD for the power pins. Meanwhile, on our panel, VSS is the positive 9 volts DC and the VDD is our GND. Pay close attention to this. We have already covered this topic several times in other videos. I leave in the description the link to a video where I try to delve deeper in this topic. I believe the panel allows the use of the 12 or 24 hours format, but I don't try to do it. We proceed with the connections, the wires to power the panel, such as a filament 1, filament 2, plus 9 volts DC, GND, and the less 20 volts DC. Furthermore, as the device had to have a switch to access clock or timer mode, it was necessary to apply a diode to the pins that would be on the switch, in order to prevent the feedback that caused the PM segment to light up. This diode application is necessary for the clock adjustment buttons to work. Also, it is essential to provide 50 Hz for the clock to work and also for it to be intermittent after a power outage. The two LEDs on the panel have a plus 9 volts DC as a common pin, with the cathodes available on the external connectors through resistors, as well as the green button, as they are completely independent from the rest of the panel. By ensuring these connections, our panel works like a clock capable of starting a timer and stopping it for up to 7 days. The use of the clock depends on the code resident of the microcontroller that integrates the driver, and is easy to deduce. We can always refer to the user manual of the device the panel belonged to for more details. This is the normal status of the clock of the hour panel, And if by any reason the power fail, when it return, our clock will be blinking. Now is necessary to proceed to the adjust of the hours, and for this we have the button of the clock, the button D set, the button day, the button start, the button stop, the button hour, and button minutes. To adjust the hour is necessary press the clock and at the same time the hours. And to the minutes is the same, press the clock and press the minutes. The change of the minutes or hours is always increase. We have the option to setting the day record, and for this we can press the day set and after the button of day, and you can go at the end. Okay. After you have the options to program the start time, and after you have the option to the stop timer. These both LEDs I connect permanent to the GND. We can control with the wires coming from the panel. This button don't have action in the panel. Go to the external connectors also. This connector here, I believe this belongs to the switch to give me access to the timer or the clock. And you can see here, I need to apply the diode between the green and yellow. This is anode, this is cathode. This diode here is necessary to activate the buttons, or some of the buttons, and also avoid the segment PM is bright. The power up of the panel is done with 9 volts DC. By this reason, we cannot power up our converter of the 5 volts to 24 volts DC. Okay, is necessary use the same 5 volts DC we use to power up the filament through these two diodes. And you can see the connector, the wires to the power up the connector coming from these 2 points, and this is 5 volts DC and this is 9 volts DC. This is the 50 Hertz. As there may be people without access to the frequency generator, I implemented a power supply capable of supplying 50 Hz. For this, I used a transformer with 2 windings, one of the 7.5 volts AC and the other of 7.5 volts AC, but with a central tap. These two secondaries associated with the two regulators 7805 and 7809 allow to obtain two complete independent power supplies, one of the 5 volts DC for the filaments and DC-DC converter, and another for the 9 volts DC to our driver. I extracted the 50 Hz through a diode at one end of the 2 times 7.5 volts AC winding, and if anyone use this method, I caution them to about the need for one resistor applied to the cathode of that diode. Of course, we don't have a clock if there is a power outage. since we depend of the 50 Hz from the electrical grid. We also cannot power it with a battery without providing the 50 Hz. Because electric current is extremely dangerous for the humans, I would like to warn you about the need to take all the precautions when working with the transformer prior connections. All points must be properly isolated to avoid any undue contact that could lead to death. Please take care with these points and proceed with the correct isolation from the wires and from the points connected to the sector. This is very dangerous, okay?